Today we're going to be talking about heating and cooling curves. So first off, you need to understand energy. And energy is the ability to change or do work. So that could be the change of arrangement, that could be the change of speed, things like that, okay? But in chemistry, we have three really places that energy goes often, okay? First off is into changing the phase or the phase energy. So every state of matter has a certain amount of energy, solid, liquid, and gas. And if we change how those particles are arranged, then we change what phase it is, which means we change its phase energy. Solids have the least amount of energy, gases have the most amount of energy. Another way that we change the energy in chemistry is through its thermal energy. And thermal energy is the energy of how fast particles are moving. Okay. Another way that we think, phase energy is the states of matter. And thermal energy, another way to measure it is through temperature. So if we increase its temperature, we increase the speed of the particles, we increase its thermal energy. And if we do slower, we go lower in temperature and we have lower thermal energy. The last way is chemical energy. And with chemical energy, it's where we rearrange how atoms are bonded to one another. So you break or make bonds. So let's say A is bonded to B, and then we add C, and now we're making A bonded to C. This is a change of A's chemical energy. Today's focus will really only be focused on thermal energy and phase energy though. What we're going to be doing is we're going to be heating up the same substance. That is why chemical energy is not really involved. Okay, why? Because it's going to be the same substance, so we're not going to be changing what that chemical is actually made out of. Okay, and so what we're going to do is we're going to start with a substance and we're going to heat it up, and we're going to record the temperature, and we're going to record any observations that we make during the lab. Okay, and there is a video to look over that if you would like, which you should look over, which is that heating up of ice. Okay, but what you'll notice is that whether I heat up any different solid, they all have a very similar shaped graph. The temperatures are a little bit different, the speed is a little different, but the shape overall is the exact same. And this is the shape that you'll get. Okay, and so what's really fascinating about this is known as a heating curve. Okay, so what we started with is down here, we started with a solid. And I put it on a hot plate. I put the solid on a hot plate, pretend it's an ice cube. Okay, it's really cold. I put it in the freezer. It gets below 0. That's where it's at right now. And then what I noticed is that I am going to heat it up. Okay, and that my temperature changes. Makes sense. I put it on a hot plate. At point B, what I actually start to notice is that it starts to have a liquid. So I notice that the solid is going to a liquid. But what's really fascinating about this is that I noticed at that time the temperature remained constant. It did not change. It flatlined. And then I noticed when it was all liquid, what happened again is that I noticed that a temperature changed. And see, when I did this, I expected, thinking it through, that it would just constantly go up. But that's not what I experienced. I experienced, which is actually true, that when I saw it going from a solid to a liquid, so when we call it melting, the thing flatlined. Okay, but I was adding heat, so this was a little confusing to me. So I'll go over that in a little bit. But then what I noticed is that, and this one's extremely obvious when you do the lab, is that at point D, when it got to this temperature, it really flatlined. And I noticed that I started to see bubbles. And bubbles mean that you are making a gas production. And it was flatlined the whole way. And if I had a closed system, which we don't, so this one is harder to actually see unless you're in a real lab, like a systematic lab, right? Like one of those high-end labs. Once it all turned gas, it actually went up in temperature again. So this is when it was all gas. This is when it was all liquid. And this area was when it was all a solid. Okay. Now, looking at this, what I want you to understand is that I am adding, yes, it is time, but I am also adding heat this entire time. No matter what, I'm adding heat. So everybody thinks, oh, if you're adding heat, you're going to make it hotter. A lot of times that is true. What I want you to note is that when I was making it hotter, I was in these areas. So this was my change of temperature. Delta means change. This is a change of temperature, and this was a change in temperature. And that makes logistical sense. It's logical. Okay, why? Because I am changing my temperature. I am adding heat. Duh, that makes sense. Okay, but these flat line areas between B and C and D and E are a little confusing to me. Why aren't they changing temperature? I'm still adding heat. Well, this comes back to the previous slide when we were talking about phase energy changes. And what happens during phase energy changes, what you are doing is you are rearranging all of the particles. And all of the energy has to go towards separating those particles and those attractions. So all of this energy, instead of the thing where it's changing my temperature, is changing my spacing. Okay? So when you are undergoing, and same with liquid to gas, so I go from a liquid to a gas, right? That's changing my spacing, okay? So there are some key takeaways that I'm going to absolutely need you to understand. First off, these are phase changes. During phase changes, there is no temperature change, okay? What you are doing is you are changing your phase energy. What you are also doing is you are spacing out your particles. Okay? Which means you are lessening the attraction between them. This is only on a heating curve. On the cooling curve, which we'll talk about, you will be creating more of an attraction. And this is the reason why is because solids have more attraction to one another, the particles, than liquids do, and liquids have more than a gas. Okay, so during this time, right here, between B and C and D and E, what you are doing is you are doing a phase change. You are not changing your temperature. You are changing the spacing of the particles because they are becoming less attractive. This also means that they are going the same speed. Why do I know that these particles are moving at the same speed? Because we measure speed by temperature. Okay, so now for these guys, it's hard for me to write all of this information on this little area. So that information applies to both B and C and D and E. Okay, this information applies to both A and D, or A and B, C and D, and E and F. So during those times, you have a temperature change, which means you are increasing the speed of the particles. You are changing your thermal energy, because thermal energy is change of temperature. Okay? You are not changing phases. Or your phase energy. Okay, the spacing remains the same. Why? Because you're liquid the entire time. Okay, and you do experience a temperature change, but you're not changing phases. Okay, now what I really want you to understand on these things is that the only time a temperature can change is when you're all the same substance. When you're undergoing a phase change, you're changing only phases and not temperature. Okay. And then I also want you to understand that this entire time you are adding energy, but the energy is going towards different things. When you are adding energy, it can either go towards changing your phase or changing your temperature. It cannot go to both. So if we add heat, at that time, you are changing phase, which means separating those particles, or temperature, not both, at exact same time. Okay? Overall, if you look at the beginning to the end, you might change that. But initially, you are not changing both your phase and your temperature at the same time. It is possible. All right. This is an example of a cooling curve. So we're just going to label it a lot more basic than on the last one. Okay. And I'm going to do it's a cooling curve. So it's the exact same thing. It's just a mirror image of the last one. So where it is the hottest, which is at point A, this would be the state of matter, because notice I am at a temperature change. So I know it's only one state of matter, where it would be the hottest, and that would be a gas. Then the next one would be a liquid. And then the final one would be where it's coolest, which is a solid. Therefore, in between with D and E, you are talking a liquid to a solid. And then between B and C, you are talking a gas going to a liquid. So notice you're taking away heat, okay? It's going down, it's a cooling curve, but it's really the mirror image, okay? Now, once again, during this time, you experience your temperature change, temperature decrease, which means you are changing your thermal energy. It's actually going down also. All same phases, all same phase, meaning you are not doing a phase change, okay? This also, just to let you know, we are changing our potential temperature is kinetic. Because we are changing our speed, so we are decreasing our speed during these times of the particles, we are decreasing our kinetic energy. Okay, that is during the when they are all the same state of matter and they are changing that. Now during these guys, we are no temp change. Once again, okay, we are decreasing the phase energy. Okay, why? Because gases have more energy than liquids, so therefore I'm decreasing it because I'm going from a gas to a liquid. They are all the same speed. I am decreasing the spacing in between particles. Because I am decreasing the spacing and the attraction, I am increasing the attraction actually, increasing attraction of the particles. Because I am increasing the attraction, because they're going from spread out to closer together, I am increasing its potential energy. So notice during this time, as I go throughout this whole graph, I decrease my kinetic energy and I'm increasing my potential energy as we go out through the whole thing. So point A has the most kinetic energy, F has the least. A has the least potential, F has the most. All right. Hopefully you have a basic understanding of, oh wait, we're not done. Okay, so let's label the parts of the graph that represent solid, liquid, and gas. So remember, if they are just being heated and you are only a solid, liquid, and gas, you have A to B, which would be your solid, C to D would be your liquid, E to F would be your gas. Okay, this one is where our phase changes. Well, that's when we're flatlining, so we're going to go B to C and D to E. B to C would be solid to liquid, liquid to gas would be D to E. Where's the kinetic energy or thermal energy changing? Kinetic energy is motion. So that means that we're changing its motion, which means we're changing its temperature because that's speed. So those would be found where anytime you are changing your kinetic energy, you're changing your speed, you're changing your temperature. So that would be A to B, C and D, E and F. And then label the parts of the graph where potential energy is changing. That would be B to C, D, and E. All right, hopefully you have a basic understanding of a heating curve. Really understand that during phase changes, you are not increasing your temperature. The only thing that they are doing is changing the arrangement of the particles, how close they are. And then during any temperature changes, they all have to be the same state of matter. Have a great one.